So we've talked about using or solving partially separable differential equations. We need to make sure that we know what it means for a differential equation to be separable. So in this top example on 123, it says determine whether each of the following differential equations are separable. Okay, well, I think I'm just going to start off each time by multiplying both sides by dx. And what I need to remember is that this junk over here on the right is grouped. So when I multiply both sides here by the differential of x, I get dy equals x plus y grouped together dx. And so here's the problem, is that y and x are stuck in that group where we're grouped by addition, and I cannot isolate, or I cannot get the y variable over to the left-hand side. Like I need my y and my dy on the same side. So I'm going to go ahead and say no. This is not a separable differential equation. All right, for that second one, again, same thing. I'm going to multiply by dx on both sides. So we get dy equals xy e to the x squared, all that junk times dx. Well, that's all multiplication. So it turns out that even though I wrote parentheses and I grouped it, we know that multiplication is like something that is commutative and associative, so I don't actually need those parentheses there. So because we actually can divide both sides by y here, we can separate. So we're going to go ahead and say yes. And then this third example, these always look confusing to me when we have a y prime. So again, just replace y prime with dy dx. Use Leibniz notation. So 2 dy dx minus xy equals 0. Well, I could add xy to both sides. So again, I'm just trying to isolate dy dx first. I could leave the 2 actually on whatever side I want. All right, so 2 dy dx is xy, or if the 2 is bothering you on the left, you could write dy dx is 1/2 xy. And this now looks a lot like that other example, that when I multiply both sides by dx, I have all multiplication. So because I don't have addition or subtraction there like we did in the first example, I don't actually need those parentheses. So since I can in fact divide by y, we're going to go ahead and say yes, this is also separable. All right, moving down the page, for 120 on page 123, this next big example, we're going to skip this for now, only because it involves an integration technique that we have not yet learned, because in 2025 we're doing Unit 8 before Unit 7. So in the future, if I switch them back, I'm sorry for skipping this one, and someone remind me about it in class. So, all right. The middle example though, so we're only going to look at 2 more examples and then we'll be done. We are asked to find y equals f of x. And again, we're looking for a particular, not a general solution, meaning there should absolutely not be a plus c in our final answer. We are given the differential equation y prime minus 3y equals 0. And we are given a kind of gross, that's a real mathematical term, yucky, initial condition that f of 1 is 4e to the 5th power. So sometimes it helps me to write that as an ordered pair to remember that 1 is my input, or my x, and my output is my y. Okay, well, we're going to do the 4 steps. We're going to separate, we're going to integrate, we're going to solve for c, we're going to isolate y. So, excuse me, when I write this down, I'm going to right off the bat replace y prime with dy dx. So dy dx minus 3y equals 0. And so in order for us to separate, we do need to first isolate dy dx. So that's not hard. Just add 3y to both sides. Dy dx equals 3y. And then again, if I multiply by the differential of x on both sides, I get dy dx equals 3y dx. But I need all my y junk on the same side, so I need to at least divide both sides by y. If you wanted to divide both sides by 3y, you could also do that. I'm going to leave the 3 on the right. So I'm going to write this as 1 over y dy equals 3 dx. and we have successfully separated our variables. So we said that's all step 1. Step 2, we're going to integrate. So I need to have my definite integral. It's very important we don't forget the dy and the dx when we do this. And we said the actual integration step is to find the antiderivative. So I have the natural log of the absolute value of y equals 3x plus c. That wasn't a really hard antiderivative rule, so that's good. Again, you cannot forget the plus c. You only really need it on one side. It's not wrong to put it on both, but it's unnecessary. Put it on the side with x. All right, so usually here, the next thing I would try to do is I would try to find c. Like I like to usually find c first and then solve for y. So if I pull this over to the right, if I plug in 4e to the 5th power, so like the natural log of 4e to the 5th power, I don't know, that's a positive number, so I'm dropping the absolute value. That equals 3 plus c. Here's the thing, if I keep rolling with this, I'm going to have c equals ln of 4e to the 5th power minus 3. And while there is actually nothing wrong with that, that just seems uncomfortable for me. That seems kind of yucky. That seems like I might catch myself making a mistake later. So what I might do here instead of solving for c first, I might isolate y first. And if I isolate y first, I'm going to get a different c later since I will have manipulated this equation first. So this is kind of a different order than the first two examples where we isolated y last. All right, so again, we've got the natural log of the absolute value of y equals 3x plus c. And to isolate y, I know I need to exponentiate both sides. So on the right, be careful, 3x plus c is the entire exponent. You cannot give it 2 e's. You exponentiate both sides of the equation. So we know that e and natural log are inverses. They undo each other. So we're left with the absolute value of y. And we also remember that we could rewrite e to the 3x plus c as e to the 3x times e to the c. We're just using the properties of powers and kind of working backwards. Now here's something. E to the power of c, that's just a constant, right? I don't know what it is because I don't know what c is. But a constant I don't know is a constant I don't know. So what I like about this is I could just call that c. Like it's a different value of c than what we had before. And I could just think of this as c times e to the 3x. So again, e to the power of c is just some other constant. All right, so finally, to get rid of the absolute value here, well, if I think about it, I would normally rewrite this as y equals plus or minus c times e to the 3x. But since we have not found the value of c yet, we do not know yet if that number is positive or negative. So we could actually ditch the plus or minus here. Ooh, this way is way easier. We could ditch the plus or minus because we will inherently find out if c is positive or negative when we plug our initial condition in, and that's what we're about to do. So, all right, so when we plug in our initial condition, we are substituting, let me try to pick a different color so this stands out. So this is now our 4th step where we're going to solve for c. We reversed steps 3 and 4. 1 and 2 have to go in order though. We're going to plug in our initial condition. So I want to do it just where I left it off. 4e to the 5th equals c times e to the 3x, and x is 1. So times e cubed. So again, if I'm solving for c, I need to isolate c. I'm going to divide both sides by e cubed, and I'm going to get that c equals 4e squared. So again, in the same exact spot where I left off, right here, I'm going to plug in my c. Y equals 4e squared times e to the 3x. And again, using those properties of powers, like x to the a times x to the b equals x to the a plus b, we learned those in middle school, I can add the exponents. So I get y equals 4e to the 3x plus 2. that is our final solution to that differential equation. So we could check that by, plugging in the ordered pair 1, 4e to the fifths, making sure it checks out. We could check that by taking the derivative of y and making sure that what we get was our differential equation that we'd get our y prime that we started with, which is 3y. Or we could just know that the answer is correct because I worked it out already. So, all right, this last example. This one is just a tough read. It's not that hard of a problem though. The rate at which a population grows is proportional to the population itself. The rate at which the population grows is proportional to the population itself. If the initial population is P naught, when I say P naught, I mean that, find the function P of t that models the population for any given time t. This is a heavily coded example where we're asked to find, again, the particular solution. So we do have an initial condition here. The initial condition is right here. When my input t is 0, my output is P naught. All right, rereading the first sentence, the rate at which a population grows, well, isn't that describing P prime of t? Like the rate at which a population grows, or I could think of that as dp dt. That is proportional to the population itself. So going back to like in 7th grade math, you learn about proportional relationships. And like, for example, if x and y are proportional, they have a constant of proportionality. So k is the constant of proportionality. And if that's if they're directly proportional. If things are like, if they're, gosh, why can't I think of this word? You know what? Forget it. It doesn't matter for this. But if they're directly proportional, that's going to be where y is k times x. So it's almost just like thinking of slope. But we learned that a while back. This is just like a harder problem. So the rate at which the population grows, dp dt, is proportional to the population itself. That's the equation we need. So p, population, times some constant k, is equal to dp dt. All right, so from there, I bet we can get the hang of this. So same 4 steps. We want to separate our variables. Well, dp equals k times p times dt. I need to get p to the other side with dp. So I get 1 over p for population. So it's kind of like y equals k times dt. Oops, I forgot my dp. That's not good. 1 over p dp equals k times dt. All right, then we want to integrate. And remember, be so careful here. K is not a variable. K is a constant. So I need to treat it as such when I integrate. So I'm going to get the natural log of the absolute value of p equals k times, whoops, not x, t. So k times t, where t is a variable, plus c. All right, so that was our second step. We said we're going to separate, then we're going to integrate. So now we're going to solve for c and or isolate y in any order. I'm going to argue this problem looks a lot like the one we just did. We have natural log on one side. We've got some junk plus c on the other side. I think isolating y here is going to be easiest again. If you want to try it a different way, go for it. It doesn't actually matter. So I'm going to I'm going to try to isolate y. And in this case, when I say y, I mean p. Okay. So if we isolate, we would have to exponentiate both sides. I guess I should do that down here. And just like that rule we talked about a second ago, I get the absolute value of p, but I could think of this as e to the kt times e to the c. And again, e to the c is just another constant I don't know. So I get this. So the absolute value of p is equal to c, the constant I'm looking for, times e to the kt power, where k is the constant of proportionality. So again, doing it this way, I can just drop my absolute value bars. I don't have to worry about plus or minus c, since we have yet to find c. So I don't know yet if c is positive or negative. So we will figure that out when we find c. All right, now we need to plug in our initial condition. So we said that when t is 0, our population is p naught. So p equals c. Oops, sorry, I forgot this should be p naught. It's kind of hard with all the p's. All right, p naught is c. Oops. Okay, all of a sudden my OneNote's not cooperating. I think my computer's overheating. C times e to the power of k times 0, which is just 0. E to the power of 0 is 1. So c is just p naught. So coming back to this, we get p equals p naught times e to the power of kt. And that is it. That is our solution. You might notice that this actually looks like a something that you learn in Algebra 2 when you're finding compound interest. You might learn that kind of like a part where you have your principal times e to the power of like your rate times time. That's not unrelated because that has to do with something growing in a proportional way. So just something to think about there. All right, this concludes the 8.3 solving differential equations preparatory work.